Hello, sir. You're not audible.
Okay, so I hope you can hear me. So today we'll discuss conjugate function. Okay, and this is how it's defined. So let f be any function from Rn to R, then f star from Rn to R is defined as follows. So where f star y is supremum of x in the domain of f, y transpose x minus fx. So this is the definition. Okay, this is how it's defined, but there is an intuition behind defining this. I will explain that. Okay, so for the moment, this is how the conjugate is defined. The domain of the conjugate function consists of all y in Rn for which the supremum is finite. Okay, for which the supremum is finite. So domain will be naturally the values of y for which function takes valued values. In other words, function values are some finite number. So that will be the domain. The domain. So this is a function of y. So the domain of this conjugate function are the set of all y for which this supremum is finite. Okay. In other words, the difference y transpose x minus fx, which is this one, this is bounded above. So if this is bounded above, then we will get some finite value. Okay. So this is the definition of conjugate. Okay. There are some geometric intuition behind conjugate. Okay. So to do that, I can. Before doing that, some remarks. So f star is a convex function. Okay, since it is a pointwise supremum of a family of convex function. Like, why is that, right? So why f star will be a convex function? Okay, so this is of the form supremum of these functions. Okay, so in other words, the way to write this will be supremum. What we are trying to do is, and this is supremum over all the x, right? So let us say like some arbitrary points x are there, right? So let us say we number them. Like technically we may not be able to number because they may not be countable. Okay, but it's something like this. So y transpose x1 minus fx1. Okay, and then y transpose x2 minus fx2 comma and so on, right? As I said, you may not be able to enumerate x1 x2 because the domain may be like uncountable, but nevertheless what you see is like you have to take a supremum over these functions, and these we see this. Okay, so we see this like these point the here x1 is fixed, here x2 is fixed, and so on, and these are like supremum of these functions, right? So these are supremum functions, right? So we can treat this as some let us say g, and then this is like g1, and this is like g2, and so on. So this is like g1, okay, and this is like g2 function, and so on. Okay, and then you have to take a supremum of this. Okay, so if gi's are like, so this is the result that we have seen before. The supremum of the convex functions is convex. Okay, so if it happens that gi's are convex, so if gi's are convex, then supremum of these g1 g2, okay, will be convex, is convex. Okay, so this is something like we have seen this before, like supremum of the convex functions is convex, like this can be proved. So this is the comment that is made here. Okay, so this is the supremum of a family of convex functions. Now the only thing now we have to see is like, are these g1 g2, in other words, are these guys convex? That's the thing that we need to verify. So are these convex, right? And we are seeing this as a function of y, right? So the only thing that is left is, are these guys convex as a function of y, right? So what do you think? For a fixed x, right? So for a fixed x, is y transpose x minus fx convex. Okay, so what do you think? Is this a convex function as a function of y? So what do you think? Tell me.
Yes, sir. It should be convex.
Should be convex. Any reasoning behind this?
Like if we take like say 2 points x1 and x2. Okay, sorry, the x is fixed, right?
This is a function of y, yeah. So you have to take y1, y2, yeah.
Yeah, so yeah, so if we take y1, y2 and like say lambda1 y1 plus lambda1 lambda2 y2 and put it in that function, so that we'll be able to split this part, but like this constant remains again, f of x will be there.
Yeah, it will be there. Like I see this as a function of y, right? So let us say this is some function of y, hy is y transpose x minus fx. Naturally, since I'm seeing this as a function of y, x will be treated as a constant. So is this a convex function, right? So how do you prove that? What was the criteria that to prove convexity of a function? Do you recall this? Like these things you have to remember, right?
Lambda y1 plus 1 minus lambda y2 should be in like should also exist.
Should exist. Why? I mean, where is
Like
the? I will always also remind that you should not mix convex function with convex set definition. Here we are talking about function, right? So convex function criteria you have to apply, right? So
Yes,
when
yes.
did you say a function is convex function?
h of lambda 1 y1 plus lambda 2 y2 should be less than or equal to lambda 1 h of y1 plus lambda 2 h of y2.
Okay, so yeah, in our usual notation, we can write like this: h of theta y1 plus 1 minus. So we are using theta usually. Is so the curve joining h1 y2. Okay, so the function values on the curve joining this must be below the line joining hy1 and hy2. Okay, so this is what we have, right? So you can check this. Okay, you can check that this inequality will hold. Okay, so this is something I will leave it as an exercise because I've done quite a few convexity proofs, but there is a easier way to claim this. An easier way to claim this is what? Easier way to claim that this is a convex.
Second order derivative.
Second derivative is what for this? Yeah, if you assume, yeah, I mean fx is anyway constant, so we don't care about differentiability of f or anything because so second derivative will be how much? Tell me. Today there will be tutorial on matrix derivative, so better do this because derivative for high dimensional things is something we need all the time. Okay, so if you take the gradient, so first derivative will be gradient, right? Of this with respect to y, obviously, because it's a function of y. So when I talk gradient, it will be a derivative with respect to y only. So if we take derivative with respect to y, right, what will be left here?
X.
X, right? And this guy will go away because that will be 0, okay? And then if we do go ahead and do one more, so this is like grad square hy, then what will be left?
0.
0.
It's 0, right? So what does it say? Like, so second derivative test, right? What was the thing with second derivative test? Like what was the criteria we needed? grad square fx was, what was the thing we needed here?
Greater than equal to 0.
Greater than or equal to 0. Okay, so obviously like equal to 0 is there, so it does satisfy the this inequality with the
Not
equal.
convex, right?
Not strictly, yes, not strictly, but convex. Yeah. So in general, we will say that it's convex, but not strictly convex. Yes. So there is a second way that we proved. I can say that there would be a third way also, that we should be like first order convexity also should be possible. Okay. So first order convexity, like what was that? Fy is greater than or equal to fx plus grad fx and then y minus x. Okay, something like that. So first order convexity also can be used, and even more simpler is like by seeing the pattern of this function. And I know that certain functions are always convex. Like I know that like linear functions are always convex. So it is a linear in y. Okay, so this is a linear function of y. Okay, this is a linear function of y, so hence it's all linear functions. We have proved before that all linear functions can be written in this form, ax plus b. Okay, and then it is convex. Okay, so this is something we know. Okay, so yeah, so there are various ways to look into this. So what we observe here is that we are taking supremum of these type of functions, and this is seen as a function of y is convex. Okay, because x is like a constant and fx is also like a constant. So it is a supremum of linear functions, and in other words, it's a supremum of convex functions because linear are convex, and supremum of convex function is convex. Okay, so this is something we have done before. Like we have done something with the max, but it's the same thing. Like supremum is like a max. Okay, so that can be extended to supremum also. So supremum of convex function is convex. Okay, so it is a convex, so that we are sure. Another thing is like f star is convex regardless of whether f is convex or not. But this holds with our discussion so far. Like we never assumed anything on f in our any of the proofs that we see here, whether it's second derivative test, okay, whether it's seeing this as a linear. No way f has any role because f is a constant. Okay, it's f becomes a constant because x is fixed, right? We are taking supremum with x fixed, okay, and so on. And then we have for different x we are getting different. So this becomes a fx has no role here, okay, because it is seen as a function of y. So fx is like constant, so it plays no role. So that is why regardless of f being convex or not, this f star is convex. The conjugate of any function is always convex. Okay, so that is interesting because this is telling us that given a function which is not convex, so for instance, I may get a function like this, okay, and I know that it creates issues for me in the optimizer because if I use a gradient method, then I know that gradient follows this, and then at some point the gradient becomes flat. I plus 1, I put xi minus alpha grad f xi. Okay, so this is what I do. So as I'm getting closer and closer, the gradient is also becoming flat and flat. So at some point at the local minima, the gradient will become flat. So this will become 0. And then there will be no more updates for you. Although you know that your global minima was here, but the gradient descent method does not allow you to move beyond this. Okay, unless you do some tricky stuff like heuristic exploration. So maybe you do some perturbation here and then you start again. But if you are here, then you will come back here again because gradient will pull you here. But if you are exploring somehow, then you are moved here, and then from here, then it will take you to the gradient will take you to this. Okay, so you can do this randomized perturbation in your X just to explore that. Are there other ways to do? But the problem is like in a very high dimensional problem. such explorations are not easy to do. Okay, let us say you have a 100-dimensional problem, 100-dimensional curve. It's like, so there are like infinite possibilities to jump over, because there could be a valley somewhere here, but there could be a valley in somewhere here, there could be a valley in this direction, there could be a valley in this direction. In this direction it might be increasing, in this direction it might be increasing. So in a higher dimensional problem, even explorations like this, that like you will say that, okay, I am at Logarithm, let me explore a little bit by doing a random perturbation in my current xi, and just to see if there is another valley I can jump into, and then I will start descending again. So there is a problem here. If it is not convex, then you get into a lot of issues like this, okay, where you are not really sure, you are lost. Okay, so what this is saying is like you can always form a conjugate of your function. So this is my fx, and what this is saying is like you can form a conjugate function where it's nice, like it is like a convex function. So it's like a ball shaped. Okay, and you solve your problem here. Okay, and then you get into nice minima here because f star is convex. Okay, and then you have a way to like somehow now go back and translate your problem. Let us say in the y domain you found the optimal point, which is y star. Now you have some way, let us say, and that will be discussed in the duality chapter. You have some way to actually go back. Okay, actually go back and find the corresponding x star that you wanted to find. Okay, that you wanted to find eventually in your original problem. That's the goal you had, right? So I'm just giving a very far ahead goal of all this conjugate function utility and so on. Why people define this? Okay, so these are like mathematical tools you can think of where you want to transform your problem into a convex problem, then gradient method can be used, and then you come back. Okay, so that is one of the motivation you can think of for conjugate function. Okay, because it guarantees the convexity. And important thing to note here is, although it guarantees the convexity, what are the things you are losing? Remember, max function is not convex. I mean, not differentiable. Okay, so you can already see some of the issues that you may face. So let us say this was there and f2x. Okay, this is convex, this is convex. Max function is convex, but not necessarily differentiable. This is like not necessarily. So those who cannot watch video, let me annotate everything. So not necessarily differentiable. Okay. So that is the problem with max function. Okay, because max function could be like this, right? So this is my one of the max function, right? And then I could have another convex function like this, right? So the max of this function, so that this is like f1x and this is like f2x. So the max of this will be, so let us say we start from here. Okay, so this is our domain, let us say, and this is our domain. So if I take max of these, well, this is the max out of these two function. So it is max until here. And then from here onwards, the other function is the max. So we take this. But the problem is that it created a corner here. Okay, so there is a corner here. Okay, corner or kink. Sometimes people say kink. So there is a kink here. So not differentiable. This implies not differentiable here, because wherever there is a kink, we know that unique tangent is not defined. So this function is like this, and there is a kink, and then it goes like this. So there are like multiple tangents possible, hence the derivatives is not possible here. Okay, so max function is not differentiable. Okay, so you already see some of the problems you may face, although it's looking very nice and that, oh, okay, I get into nice convex function, but you may be losing the differentiability now, which can create issue for you, because if you want to use gradient method, you are requesting for differentiability, right? So the usual differentiability will not work. Okay, so for a problem with kink, okay, we need sub-differentiability. We need sub-differentiability. Okay, so sub-differential. So that's that's something we will discuss later on for non-smooth optimization problem. Okay, so these are part of non-smooth optimization. Non-smooth means non-differentiable optimization problem. Okay, so these are also the issue I have already pointed out in advance for you, like what are the issues one may face, but it's not a like lost, everything is lost here, because there is a concept of sub-differentiability. So even if I go to the dual, convexity is guaranteed. Now differentiability is not guaranteed, but I can work around with a tool called sub-differentiability, okay? And then I can still do something like gradient descent, which is provably convergent, okay? So we will see some proofs also of later on. So, okay, so now we will come back, okay? And focus on conjugate function, like how to find conjugate functions, okay? So that will be our focus. But before that, I will give you some geometric intuition behind this, okay? Okay, so the important thing to note is the conjugate function is convex regardless of the given function f being convex or not. Okay, so that's something we recall. So let us look into a little bit of history and geometric intuition behind conjugate, and that will like put the ideas a little bit more firmly in your head maybe. So let us see. So it has connections with supporting hyperplane. So supporting hyperplane, remember what was the supporting hyperplane? So recall, these are the examples and non-examples of supporting hyperplane. So this is an example of a supporting hyperplane. So it's like a plane that just comes and touches one of the points of your set. Okay, so supporting hyperplane could be defined for any arbitrary set, obviously, but the restriction was that whole of the region must be on the one side of the supporting hyperplane. In other words, it should be along the normal. Okay, so the body of your the convex set, the region should be on the side of the normal of your supporting hyperplane. Okay, that's how it's defined. Okay. Okay, so like this is not supporting hyperplane because it's not yet touching, right? But the moment it touches one of the point and whole of the region is on the one side, along on the side where the normal of the plane is pointing. So this is the normal of the plane. Okay, then we know that then this will be declared as supporting hyperplane at this point. Okay. Okay, so we have seen that before. So these are some examples where it's not supporting hyperplane, because this, if I draw this, then first of all, it's not like, it's like some part of the domain is on the other side. Okay, it's on the other side. So hence it's not supporting hyperplane. This is not supporting hyperplane because it's not passing through one of the points. Okay, so that's why this is also not supporting hyperplane. So not passing through one of the points, through one of the points. And here this is again not supporting hyperplane because your normal has different direction. Okay, your normal should be pointing in the direction of the set in which it's there. Okay, so the last one is not, because the normal is pointing outwards, rather it should be inwards. So we define this as inwards and this is outwards. Okay, so what we know is that for a convex set, there at each point we have yeah.
Sir, is it the conjugate of the conjugate is the original function?
Yeah, so conjugate of the conjugate, is it the original function? Not in the most general sense. Okay, so I will tell you with some example. Conjugate to conjugate may not be exactly the function. There are some conditions, additional conditions needed. Okay, so I will let you let you know about this. In fact, this is something I plan to discuss. Okay, so but yeah, so there are some additional conditions needed, and based on that, then we can claim. Okay, so
Hello, sir. Once
yeah.
can you explain the last case, like the last diagram? Yeah, the last case. Yeah.
Yeah, so here, like, remember the way we define supporting hyperplane is that the normal should be inside this way. Okay, so normal should be pointing inwards to the region. Okay, and this is coming because of the inequality that we assumed in the supporting hyperplane. Okay, So it's like the points here should be making the acute angles. Okay, so because I take any vector here and it makes acute angle. Okay, so that's fine. Okay, if I take here, then it making the acute angle. So the inequality that we had was like less than equal to, right? So that's why it means that the normal that we have must be making the acute angle, right? So A transpose of the values that we have here in the region, right? So their angle that they have, it must be acute. So that's why this inequality was, I think, less than equal to 0, okay? Because it's making the acute angle. So then we claim that A transpose X is a supporting hyperplane. If your this was this, then your definition is violated. Okay, so it in other words is saying that A is pointing inwards. That's why this is satisfied in the definition of the supporting hyperplane. So that is the reason why. Okay, I mean this is coming from the definition. Like we define it in a way that it will be pointing, the normal will be pointing this way. Okay, remember a plane, I can always define either this way or this way. Right, it doesn't matter. But in our definition of the supporting hyperplane, we claim that this normal is pointing in the direction of the of this where the region is. Okay, and that is why this inequality is like is satisfied. Okay, like if you
Sir, in the last
let us say
diagram, how are you drawing normal outwards? Like,
sorry.
why can't it be inwards? Like in the third case, how exactly are you drawing normal?
Yeah, so the normal is this way, right? So it's like the other way, like minus of A, right? So here the way I have described this plane is like minus of A and then X, right? So the plane could be seen as this with this normal or with this normal, right? So the way we require in our definition is that it is with this normal that is pointing inwards, not outwards. It's coming from the definition of this hyperplane. Like a hyperplane is what? A transpose X is equal to B, right? So that's the hyperplane, right? So another way to write the same hyperplane would be minus of A transpose, minus A transpose X is equal to minus B. Okay, so the same hyperplane, I can see this as A transpose X is equal to B, but I can also see this as minus A transpose X is equal to minus B. Okay, but when I'm saying that it's a supporting hyperplane to some region, then I'm asking for the plane normal to be in this direction. Okay. Okay, that's like the convention we are assuming, that by convention we assume the normal to be in that direction. Okay, so it's a matter of convention, I would say. Okay, it's like if you describe this plane with reversing this. Okay, so if you describe this plane by reversing this, so you just take minus of this, then it is the plane described by this normal, because plane is described by a normal. Okay, and of course the intercept also so if you just change things in your it's a convention thing, so change this by doing the minus both side, and now it is a proper hyperplane we are talking about. Okay, although it is the same thing. Okay, but it's just that we want our, so I will redefine my A to be this, A tilde X is B tilde, and then I will say, okay, now it is fine. I needed minus A, so I multiplied both sides, and now my normal is pointing this way, and now it is fine. Okay, because then it will go well with the definition of the supporting hyperplane. Okay, so it's like by
Yes,
convention,
yeah,
by convention we want our normal by convention. Okay, I mean this would have been a supporting hyperplane if you had redefined your normal in a way that it points inwards, not outwards. Okay, this is a convention thing. Although the plane is the same, but the way normal is pointing in your plane matters. Okay, for the inequality to correctly satisfy. Okay, so so what we know is we have not done this proof, but what we know from intuition is that in a convex set, at each point I have a unique hyperplane passing through that. Okay, so in a convex set, I can choose any point, and I will have a unique hyperplane passing through that. Okay, that is the tangent that passes through this. So what this is trying to tell me is that in some sense I can approximate a convex set by a collection of these supporting hyperplane. Okay, by collecting these supporting hyperplanes, I can somehow approximate a convex set. Okay, so in other words, like it's a collection of supporting hyperplane that is enough for me to describe. I mean, I have to take a lot many of these. Like there will be. I'm sorry. I'm sorry. So there will be a lot of this because this is like there will be infinitely many hyperplane, right? But that's the intuition. Like I can enclose the convex set using supporting hyperplanes. It could be infinitely many. Okay. So this is something we know. There is a unique supporting hyperplane at each point in the convex set. Okay. So if we now translate our convex set to epigraph, right? So now we define now we translate our intuition to function. Okay. So supporting hyperplane, let us say for function. Now we know that if a function is convex, the epigraph, which is the region around this, which is shown by line here. So this is a convex epigraph. So that's something we know. If it's a convex function, then the epigraph is convex. Now, as a set, epigraph is a convex set. And from the previous definition, we know that a set can be like have a supporting hyperplane because supporting hyperplane concept applies for set. Okay. So from convex function, we go to convex set, which is the epigraph of the function. And then for that convex set, we will have supporting hyperplane. And these will be unique, like for each point in the graph. Okay, so there will be one supporting hyperplane, unique one, because this is part of the convex set. Okay, so hence I can draw tangents at each point uniquely, and those will be indeed the supporting hyperplane. Okay, and those will be unique. So that's something we can conclude. Okay, a closed convex X is uniquely defined by a lower hyperplane. So for a convex function, what we observe is that these will be all lower because of the nature of the function. It's convex. So what we are getting is like the set of these lower supporting hyperplane. Okay, now do you see where we are going, right? We started with conjugate functions, right? We started with conjugate functions, and out of nowhere we said we defined something with conjugate functions, and then we are now looking into supporting hyperplane of the sets. Okay, we are looking into supporting hyperplane of the sets, and for a convex function, what we know is like we can support this convex function. Okay, in other words, we can approximate this supporting this convex function via a collection of supporting hyperplanes. Okay, so there is something deep going on here. Okay, so let us see what we can get next. Okay, so we have not related completely with conjugate, but let us see. Okay, so now this is the most important slide for conjugate. Okay, so let us see what is happening here. This relates supporting hyperplane with conjugates, and overall the idea is dualities are nothing but space where you have a collection of slopes or the plane. Okay, slope, like in the 1D case I'm saying slope, but it's the collection of the hyperplanes. Okay, and it's like the supremum of these, and that is where like you may want to solve via duality. Okay, so like that's the very top level view. Like it's already we are jumping into something. So so what I'm trying to say is now the following. This looks very I mean, very similar to conjugate. So conjugate, the way we defined was like, this is the 1D case, right? So this is Rn. And the conjugate, the way we defined, recall, so it is a good thing to actually write that conjugate here also. So that was in Rn, right? And here we had y transpose x minus f of x. Okay, so this is what was the conjugate, right? So this was f star. Okay, this is conjugate. Okay, now we will go. We want to get to the intuition, but it's not easy to visualize high dimensional. But so we will restrict it to R and try to see what role conjugate plays. Okay, and we are going into like we wish to go into some other space where things are nice, in the sense that it's the conjugate function is convex, and that helps in the optimizer. Okay, so in the 1D case, let us see what this means in 1D case. Okay, the 1D case means like x is some some real number. Okay, and this is supremum of mx. So here this is like a y. Okay, so for a real number, y transpose is just y. So that's why I don't have to do m transpose here, right? So this is like yx minus fx. Okay, so here you can think of this as y in the conjugate. Okay, so what this means, right? What does this mean? So I have a figure here. Okay, so this is the blue one is a figure of fx. Blue one is a figure of fx, and we are supposed to find a supremum of these guys, right? Mx minus fx, right? And x will be something I will like fix and then check. Okay, this is one function, and then some other x, this is another function, and so on. And then I have to take a supremum of all this, right? So if I see just mx, if I see just mx function, then this is like a line. Okay, this is like a line passing through the origin. Okay, so this is like a line passing through origin. Okay, so in this case the origin is 0, right? So what this is trying to say is like mx is a line passing through the origin, like this is some mx, and for one x this is this, for another x this may be different, and so on, right? So this is the line passing through the origin, and this is my function fx. And what I'm trying to say by doing supremum is like what is the maximum gap that I will have, because that's when the supremum will be achieved. Like what is the maximum difference between mx and fx at a point x. Okay, so that's when I will get the supremum. Okay, so in this case, if you see this example here, I have a line with slope m. Okay, and then what I will do is that I will parallelly like move this line, okay, until the point I hit fx, because fx must be a point on f, right? So I cannot go like so this x must be achieved, so this must be fx here, right? Like you will say that why not I move here, but that is not, but this is not the function value taken by fx. I mean here, this is not fx. This is not fx, right? Or this is not fx, right? So I have to stop at a point where there is fx. Okay. So what this is trying to say is like how far you can go, how far you can go. In other words, the supremum, how far you can go from mx, which is this, for the given x. So this is my some x. Let us say this is some x1, right? So for at x1, I have mx1, and how far I can go, right? So for varying x also, right? So it's like I keep doing this, right? So if I see this point here, right? If I see this point, let us say this is like x2. If at x2 I see, then fx2 is here, and this is like mx2. And now this difference is smaller than this difference. Okay, because this is like here in this case the line and this gap is the most. So at x1 I see that at x1 the gap is maximum, the biggest gap. Okay, the gap is biggest. Okay, so the gap is biggest. So like you have to do this for all the x. Okay, so you do this for all the x, and see where the gap is the maximum. And the gap where it will be the maximum, it will be, in this case, in this example, is this point here. Okay. So it will be this point here, and that will be like the so that will be the point where like I'm looking for exactly this this point. I mean this hyperplane. I mean, okay, that so. And I know that if the function is convex, then this will become a supporting hyperplane, because any tangent for a convex function becomes a supporting hyperplane. Okay, so like that, so that will tell me that this like supporting hyperplane. If f is convex, obviously, right? If f is not convex, then we don't know, right? It may not be. Okay. Okay, so so what this is giving, what this is telling us is that the conjugate functions are like the supporting hyperplanes. Okay, I mean they are parameterized by the slopes. Okay, so they are parameterized by the slopes of the supporting hyperplane. Like, I mean, you can think of slopes of the supporting hyperplane, like this guy have the same slope, right? Okay, so the another way to look into the conjugate functions are like collections of slopes. It's like you are going from the x domain. So this is like a primal. Okay, so let us say your primal, like the prime variable of your domain was x. Then you went to a other space where, let us say, you call it dual. In the dual space, you have converted your problem to slope domain. I call this slope domain. It may not be a like standard terminology. Okay, so you may not find this thing in the book or something, but just for like intuition, what I'm trying to say is like you solve your problem from x domain to something like slope domain. I call it slope because the conjugate functions are like functions of the slopes of your hyperplane. In other words, they are in the higher dimension. Rather than saying slopes, we should call it normal. Okay, so it's like the normal vector domain. Normal vector domain. Okay, these are not standard words. Okay, so don't quote me on this that I told you this and so on. I'm just saying this for your intuition. Okay, so what the conjugate function is trying to do is the following. So far, like we have not seen the use of conjugate function yet, but so far geometrically what it is trying to do is like it is transforming our problem from x domain, which we call it primal domain, to a normal domain. Okay, normal vector domain. It's like a collection of all these slopes that you will have. Okay, all these slopes you will have, that will determine, because m I will keep varying, right? So this is the first m I chose, right? And then I may choose some other m like this. Okay, so this is like some other m2 because this is my slope domain. So this was my first m1, let us say. Now I created another line passing through origin m2, and now I start playing with this x1. So I will say x1, okay, what is the maximum gap? Okay, another x2, what is the largest gap? So this is the gap. Another x3, let us say, what is the largest gap I have? So this with this or something. So I have to find the largest gap. Okay, so once I find the largest gap, that will determine the function value for that m. Okay, because this is a function of m, so I have to tell each time for m1 what is the function value, for m2 what is the function value. But I know, because this can be done with this supremum. It may be tedious, it may not be obvious. Okay, but we will see the rules of how to make this computing this conjugate more trivial. Okay, but for the moment, and it is possible to find this because supremum always exists. Okay, we have seen this before, so it is always possible to define this function. Okay, it's a well-defined function, and moreover, what we have seen in the conjugate definition is that it is always convex. Okay, so this is always convex function regardless of whether fx was convex or not. Okay, so that is something very important for us to know, because if I'm solving my problem in the dual space, then the f star m, okay, so this is convex. always. Okay, may not be differentiable as I said, but sometimes we will still bargain for convexity rather than non-differentiability, because non-differentiability can be handled with subgradient approaches. Okay, so there are subgradient methods where we know how to define some useful gradient. Okay, the gradient may not be unique, but we may define some useful gradient so that we still go to the minima. Okay, so so this is the thing about conjugate, and in general these are called Fenchel. So Fenchel is like again the French guy. Legendre is also French guy. Okay, so the French guys were always like prolific with this maths part. Okay, so they had these definitions. Okay, and the goal is to apply this to problems where you are suffering from non-convexity, and by applying dual you may, I mean, it's not always the case that you end up in a nice setting, but there are many problems now where it is much better to go to the dual and solve the problem there and then get back to the X domain. Okay, so remember in a larger philosophical motive, you do have primal dual things going on in other areas also. Okay, so if you are someone from electronics, then you may have seen like time domain and then frequency domain. So there it depends, like sometimes you may want to solve your problem in a time domain, sometimes you may want to solve your problem in a frequency domain. Okay, so such kind of duality does exist where you may want to go into some other variables where it's easier to solve and so on. Okay, it may also have to do with the dimension of the problem. Okay, your original dimension problem, if you go via the usual method, it may be very costly. But the moment you switch to the dual problem, it is very tractable because the dimensions of your variable that you have to work with are much smaller dimension. Okay, so this is why as an optimizer, optimizer person, you have to understand these details, like which algorithm will be suitable when. Okay, so dual is not always a good thing. Okay, so you have to understand when to switch. Okay, so far it is still looking abstract for you, I understand. Okay, so let us compute conjugates. Yeah.
F of M1 is the supremum of M1x minus f of x for all x.
Yeah. So the supremum is over x, right? The supremum you are.
Sir, here you said the gap. If you said mx1 is a fixed one, so that gap is maximum at that given x, right? Since you are considering that as the answer, you are considering f star m, right? The gap.
So
that
this
gap
point,
is the maximum for all the x given, right?
Yeah, and you have to vary x. That's the point. Yeah. I mean, first thing is,
but like here we can observe that for negative x, the gap is more maximum, right?
Yeah, it could be. Like no, for this, right? So and then we have to take the supremum. If you take negative, is it not that your sign will change? The sign will change, and then
there is no modulus. Yeah, it will be a smaller well. Yes.
Yeah. So so you will prefer to have positive and larger value so that the supremum will be there, and negative will not be supremum, right? Okay. So this has nice geometrical interpretation, and you will see that many books also doesn't discuss this. Okay, so in fact you will not find this very easily, the material that we are discussing, because none of them actually discuss this. In most of the standard books, I have not found such geometrical things. Like they just write down as a maths. Okay, anyway, so find the conjugate of the following functions. Okay, so now we talked about, okay, we can compute the conjugates, and then it's about finding the maximum, supremum, and so on. So this looks tedious at first instance. It looks a bit tedious because it's like I have to vary and then find the maximum gap and so on. So it may look a bit tedious, but let us see, like whether we can find conjugates of some well-known function. Okay, so these are the exercises that we would like to do. Find the conjugate of the following functions. Okay, so let us say affine function fx is ax plus b. Okay, so what is the f star for this? Negative logarithm fx is minus log x. Okay, so what is f star in this case? Exponential function. What is f star? Negative entropy. What is f star here? And then inverse function. So okay, so these are simple functions. It may not help to go into conjugate for these functions, but for a practice, like, we may want to know how we can find conjugates for this function, right? So so for the conjugate functions, if we can look into the definition of the conjugate function. What was the definition of the conjugate function? So let us go few slides, and this is the definition of the conjugate function, right? So f star y, which is supremum of x in the domain of f, and y transpose x minus fx, and the domain of the conjugate function consists of all y in Rn for which the supreme is finite. So the thing that we should keep in mind is, like, f star is indeed defined like this, but we have to properly define the domain. So it should only consist of those y for which this guy is bounded. Okay, so for which the supremum is finite. Okay, in other words, the difference y transpose x minus fx is bounded. Okay, so given a function, we have to look into these things, y transpose x minus fx, and we have to make sure that this is bounded. Okay, so that's the requirement when we are computing the conjugate functions. Okay, okay, so let us keep this in mind and let us go back to solve the problem. Okay. So affine function, right? Find the conjugate of the affine function. So let us do this here, right? So what we have to look at, so f star y, we recall, is supremum of y transpose x minus fx. Okay, so this is how this is defined. Okay, so what we have to look at is y transpose x minus fx, but this is a real value. So x is in R, so y transpose is just y, right? So what we look at is yx minus fx, right? So fx is ax, so yx minus fx, which is yx minus ax minus b. Okay, now the question is, remember, this should be bounded, right? So y transpose x minus fx must be bounded. So this is one condition that will tell us what to do with this. So must be bounded. Okay, so it is bounded. So when it is bounded, is bounded if, so when is this bounded, right? That's a question now. When it is bounded. So bounded as a function of y. Okay. So remember this is a linear function in y, right? So for this to be bounded, what do we need? Remember, linear functions are linear functions bounded, right? So that's the interesting question, right? So are linear functions bounded? Okay, so are linear functions. It depends on the domain, yes. Okay, so in this case, like, x is anything, right? So x is like allowed to be anything, or all of R. Okay, so now, like, so is this like bounded?
If y is bounded, it should be bounded.
Yeah. So in general, what we know is, like, the linear function, the only bounded linear function is a constant function. Okay, because that will work like this. Because any linear function you see is like this or like this or like this, that is not like constant. In general, we'll go up to like infinity. Okay, so in general will go up to, so it will be unbounded in either way. Okay, if we allow it to go either way, then it will go. So what we know is like only the constant functions are like are those functions which are like going to be bounded. Okay, so this will be bounded if and only if y, I mean it will be a like a yeah, when like, so if this is constant function, then what will I do? Right, so for which values of y it will become a bounded function?
Y equal to a.
Multiples of a, like one.
Y
Some
equals to a.
multiple of a.
Yeah.
So not exactly. It can be some multiple of a also, right? Okay. Okay.
But x,
Yeah.
but x will yeah,
Yes.
but x will make it unbounded, right?
Yeah. Yes.
So it has to be y equals to a only. Okay, so it has to be y equals to a. So is bounded. So I continue from here, is bounded if y is equal to a. Okay, then this will get cancelled and we get like minus b. Okay, so the domain of, so this is bounded if, and since this is a constant function, the supremum will be just like minus b, right? So from here what we know is like domain of f star is now just restricted to a, because that's the only valid reason for which y transpose x minus fx is bounded. So just by boundedness condition we got the domain of f. Okay, and for that domain of f there is only one point left. So for that if we compute the supremum and so on, it will always be, because there is no dependence on x anymore. So for x equals to a is only thing allowed in the domain. I mean y is equal to a is only thing allowed in the domain. So then supremum will be just minus b only. Okay, so that will be, okay, so that will be the function definition, because there was only one thing allowed in the domain, and for that value what I get as a conjugate is minus b. Okay, so this turned out to be like very trivial example. Okay, maybe useless. Okay, but yeah, so this is our first example on conjugate. Now let us see some more. So let us say conjugate of the negative logarithm. Okay, so again we always start with argument with the domain. Okay, so in this case we know that log x is defined for domain of f. Okay, so this is f is a function of x, f star is a function of y, right? The domain of f is all positive values, right? Because we know that logarithm is defined only for positive values of x. Okay, and now we will look into fy, right? So fy, the way we defined was y transpose x. In this case, again, these are real examples. So this is like y x minus fx. So this is like yx minus fx is like plus log x, right? Log x. Now, what about the bound? Okay, so again, we argument it will be through the to make it bounded, right? So let us see. So when it is bounded and when it is unbounded. Okay, that's the question. When it is bounded and when it is unbounded.
Yx should be constant.
But log x is unbounded, right? Even if yx is constant, log x will go up to infinity. It will go slowly, but it will still go to infinity. So log x will be like this. I mean, it will not touch, but it will go like this. So if yx is made constant, it is still varying with log x and goes up to infinity.
Maybe equate it to some constant c.
I mean, does not have to be like have to be constant. I would say it does not have to be constant, but it may
Some
be
bounded
decreasing.
function.
Yeah, something that is bounded. I think constant will be a too much restriction. So we have to say that this doesn't grow for any like x in positive, okay, and for any y. So let us do case by case. What if y is greater than or equal to 0? Let us say case 1, y is greater than or equal to 0. So if y is guaranteed to be greater than or equal to 0, can it ever be bounded?
No, sir, it won't be. I mean, it can't be bounded. It will go on
Why?
increasing.
Why?
Like log
Why?
x is positive and yx is also positive. Like if you consider
Yeah,
x is also positive, right?
yeah, but
Like so the
positive.
lower domain is fixed, but the higher domain can be ranged to infinite, like the higher limit.
Yeah, but positive doesn't mean it will be unbounded, right? Like you, I
Yes, sir,
mean,
it will be only one side bounded, right, sir? Like
yeah,
x
but
can reach infinity.
yeah, but how? Like, what is the rigorous argument here that fy will keep increasing? Like, are there any way to justify that fy will keep increasing if y is greater than or equal to 0?
You can take the slope.
Slope, yeah, you take the derivative, right? So if you assume that y is greater than or equal to 0, then this implies f prime y. Okay, so this will be x. Okay, and this will go away, right? Because I'm taking derivative with respect to y, and now x is positive anyway, right? So this is greater than 0. So this implies fy is increasing function. Okay, that's what the slope means, increasing function for all y greater than or equal to 0. Okay, so this will tell us that fy as a function of y for y greater than or equal to 0, this will become unbounded because this is always increasing. In fact, it is strictly increasing. So it will not even like it is not even like it will go and become flat. Then it will not be unbounded. Since it is strictly increasing, so this is like strictly increasing. So this means that it will go up to infinity only, okay? Because it's strictly, it has to increase all the time. Okay, so that's the case. So it will be unbounded, okay? So unbounded case. Okay, so the case that is left is now y is less than 0. So y less than 0, right? So for y less than 0, what is happening, right? So case 2 is y less than 0. Now, can we do some analysis on this, like y less than 0? Um, uh, what will happen in this case?
So this will also be unbounded, right?
So if y is less than 0, yeah. Will this be bounded or unbounded?
So this will also be unbounded, following the same logic.
Plus, sir.
Yes.
Sir, if we set y as some number which is close to the minus log x value, then all minus log x and plus log x will always be in small range, so it can be bounded. Right?
Um, One second, I think we are doing a small mistake here. we should see this as a function of x, isn't it? Because the supremums are done over these functions, g2 and so on, and this is varying over x. Okay, so is it not that like we are worried about these guys going unbounded as a function of x, not necessarily as y? I think we are doing this mistake here, because supremum when we are taking, we are varying y for these guys. Okay, so this will be like function of x, and then if I take a derivative with function of x, let us see what happens, right? So derivative with respect to x actually we have to take, because we are worried how this g1 g2 varies with x, because they're suprema over x. Okay, and then y is also there, but the suprema is being taken over x. So if for some reason for varying x it's going unbounded regardless of y, let us say, then it is unbounded. So like then those, like if it is for any y and it is for any y, one of them is going unbounded, then the domain will be empty. Okay, that's the argument here. So let us fix things. Okay, so what we have to see this as a function of x, because we are taking suprema over x. Now I will take derivative with respect to x. Okay, if you take derivative with respect to x, so this is y plus 1 by x, isn't it? Right. So y plus 1, but this is still positive. So our original argument still holds. So this is like something greater than equal to 0 plus something which is greater than 0. So overall it is greater than 0. Okay, so this argument still holds actually. Okay, and now y less than 0. Now y less than 0, let us see. Derivative with respect to x, right? So f prime x, I see this as a function of x. Okay. Okay, so derivative with respect to x is again like before, it is y plus 1 by x. Now y is less than 0. This is a tricky case. Okay, now y is less than 0 and this is greater than 0. Okay, not conclusive. Okay, we cannot claim that it is strictly decreasing or increasing. Okay, but is this like, can be like find a critical point or something, right? So we equate it to 0, let us say. Okay, so what is the critical point? Like where does it become flat, right? So critical point. So in this case, we have to work a little bit to see, are there like points where it's like, I mean, it is increasing, decreasing. Let us say it's not unbounded, then there must be a point where it is getting maxima or minima. Okay, if a function is not unbounded, then it must be achieving some maxima or minima. Okay, that's what we know. Okay, so that is what we are trying to try and see if that is the case. So we will find a critical point. Okay, where the tangent is becoming flat, because if there is a maxima or minima of this guy, then the tangent will be becoming flat, right? So f prime of x will be 0. So this implies y plus 1 by x will be 0. So this implies y is equal to minus 1 over x. So y being minus 1 over x, what happens? Right, now the question is what happens, right? Or like x is equal to 1 over I, other way to say is x is equal to minus 1 over y. So what can we say about this function, right? And if I do a double derivative to check whether this is indeed, like this point is a maxima or minima, it is still not guaranteed. It's only saying that the tangent is becoming flat at this point. So if I do double derivative with respect to x, right? So this guy will go away and this is minus 1 over x square. Now x is positive, right? The domain of f, which is positive. So this is like surely negative. So this implies that, I mean, okay. And like, I mean, regardless of y, okay. So, regardless of y, right? Hello. Please turn off your microphone. Yeah. Okay, so let us see this. What is going on? So f prime x is 0, right? So we have got the critical point and x is positive. Okay, so from like first derivative test does not tell us anything strictly, right? Whether it's less than 0, this, but if we do the second derivative test, okay, if we do the second derivative test, then it is telling us that like at this point, right, x is equal to -1 over y, like we can compute this f prime x at x is equal to -1 over y. So what is this? -1 over and x square, which is -1 over y whole squared. So this is like y squared only. I mean minus y squared. Okay, so this is minus y squared, and y squared is always positive, and this is negative, right? So this means that x is equal to 1 over y. X is equal to 1 over y is what? Minima or maxima? So second derivative is negative, right? So it is maxima, right? So this is maxima, right? So this is the maxima that we have.
But we can't limit the domain of X, right?
We can't limit. No, our domain of X is limited to this.
Yeah, so we can't have any more restriction on X. So we have to play around with Y.
Yes. Yeah, that is correct. But so it reaches maximum at x is equal to -1 over y. Okay, so from here what we learn is so from here what we learn is the domain of f star is the set of all y for which y will be less than 0, because yeah, so the domain of y domain of f star will be, because for any of the x, right, in this case it's well defined, okay, because there is some maxima that we are getting here, okay, so it's not like going unbounded. Okay, so it's not going unbounded. For whenever you have y negative, you are getting some finite supremum value. Okay, that's what it's trying to say. Okay, and so from here what we learn is like we can define the domain of f star. So domain of f star is set of all y such that y is less than 0. Okay, because for these guys I'm always able to find some supremum. Okay, and that supremum is like given by this these values, right? Y is equal to minus of x. Okay, so these supremum values are possible. So I'm not getting into like unbounded case here. So the domain of f star will be like plus plus but negative, like all negative values. Okay, and for which of these values of x I'm getting the supremum, these are like the values of x are like 1 over y. Okay, so the x is 1 over y for these cases, right? So if I write down fully now f star of y is now now y, and then so x is 1 over minus 1 over y. Okay, so these are the values for which I am getting the supremum, right? And then plus log of 1 over y. Okay, so if I simplify this, then this will be minus log of this is like minus log of minus y minus 1. Okay, for all y less than 0. Okay, so this is what we will get, right? So I have substituted x to be, because these are the places where it's getting the maxima, and maxima is the supremum that we are looking for here, right? So we have found places where it is indeed achieving the maxima. Like maxima is not going up to infinity. That was the worrying case for us. But as long as it's taking some finite value as a maxima, because we are talking about supremum, we are not talking about infimum anyway, right? We are talking about supremum. So the only worrying part is that it should not hit infinity, something below. Okay, so something below would be like minus 1 over x. Okay, so this is the conjugate of f. Okay, so how do we go about doing this? Like we always start with boundedness, because this is all about supremum. So we have to discard those those y values for I mean there is an interplay between x and y both here, right? So here when we see these guys, then these are like function of x, and they should not blow up to infinity for the varying x. But then it also depends what y was. Okay, so here, like in the first case, we saw that if y was greater than or equal to 0, then regardless of like what x I choose, okay, it's like for varying x, it does blow up to infinity. Okay, so when y is greater than or equal to 0, the supremum is guaranteed to go to infinity. Okay, so we have to always reason with y first. Like the cases we make are with y, and that for those cases we want to ensure like whether it is bounded for all x. Okay, so that is how we proceed. So first the cases we do is with y. So let us say what if y is greater than or equal to 0, then it is guaranteed to be going to infinity. Then we say what if y is less than 0? If y is less than 0, then it does hit some like some maxima. Okay, so it's like in this case we cannot really say for sure that it's unbounded because of this condition here, that it's like it's not monotonically increasing or decreasing. Okay, and then we go ahead and see whether there are points in the domain where it can reach maxima. So in that case, whenever y is chosen to be minus 1 over x, okay, then it hits the maximum. Okay, so y will have some kind of neutralizing effect along with x in these functions, so that it will get to something some maxima. Okay, so this is the conjugate of log of x. We have 3 more examples to play with. Let us see.
Hello, sir.
Yeah.
Yes, sir.
Sir, for the case 2, for y less than 0, why did we differentiate with x instead of y?
No, we are always differentiating with x. I think here there was an error that I started with y. I always see this as a function of y, because at the end of the day I have to see supremum of these guys. Okay, and these guys are taken supremum over x. Okay, so for some y, for all x, is it bounded? And to check that, I have to look into some of these terms, right? Like generic terms. So generic terms look like this. Now from here, like I see, okay, for different value of x. So that's why I see this as a variable of x, because g1 I get for some x, g2 I get for some other x. So in other words, I'm trying to see for varying x, is it like going unbounded, out of control for certain value of y? Then yes, because for y greater than or equal to 0, it is indeed going unbounded. Like surely it is going unbounded. So this supremum result will be infinity surely. Okay, so that's the case. So the reason why I take derivative with respect to x is because I want to understand whether these guys are blowing up as a function of x or not. Okay, because the supremum is over x, so I have to study the growth of this function as a function of x. Okay, as a function of x for fixed y. Okay, by fixed y I mean like sometimes I club everything, right? So I'm saying y greater than equal to 0. It's like I have fixed y to be some arbitrary greater than equal to 0. Okay, still fixed but arbitrary and greater than equal to 0. So I'm not really varying y. My concern is like, are these guys going to infinity for arbitrary y greater than equal to 0 and for all x? Okay, so that is why it's important for us to see these as a function of x, and y is kind of fixed, still arbitrary but kind of fixed. So then I make a global statement that y greater than equal to 0, it is surely going to be unbounded. From the derivative test, I guarantee that it's going to be, because of the domain of x and so on, it is guaranteed that the slope is positive. So if a slope of a function is always positive, that it means that it's always increasing. And if that is the case, and this is x is for all positive, so it's always increasing, it means that it will surely go to infinity because it is strictly increasing. So that's the thing. Okay, so in this conjugate thing, we try to do case by case basis. Okay, like you cannot go for point-wise thing because that will be too much to do. So usually your cases are like this: y greater than 0, what happens? Y less than 0, what happens? But doing supremum, you know that y is fixed because we do supremum over x only. So these are seen as a function of x. The outcome of this, okay, will be given, will be like seen as a function of y. Okay, so it's a combination of x and y here, but the supremum is over x, so that's why I worry only about x as a function of x. Okay, let us do some more example, and I think three more examples are there. Yeah. Yeah.
Sir, the definition says that y transpose x minus f of x should be bounded. That means that we need to select some y which will be bounded for all x, or do we need to select some subset of x which is bounded for a given y?
Yeah, actually it's like both. It's like both. It's like all possible, all x and y actually. Okay, but the way we proceed to solve this problem is like we fix y and we see this as a function of x and then see whether it's bounded or not for that fixed y. Okay, so it should be like bounded as a whole. Okay, it should be bounded as a whole, but the good way to think about this is that your y is fixed. Okay, and then you are varying x to see if it is bounded for that y. If it is bounded for that y, and then you will go ahead and change your y, and then you will say, okay, well, it's bounded for that y. For instance, here in this case one, let us say, I will choose some y1 which is greater than equal to 0. I will choose some y2 which is greater than equal to 0, and so on. I will choose many of these, right? Okay, and then I will check, are these GIs for y1? Are these GIs bounded for all x in the domain? Okay, so which is positive. So it's no. Okay, and then I go for y2. For this fixed y2, are these GIs as a function of x bounded? No. Okay, so this way I have this, but rather than doing this pointwise, I say regardless of all the y positive, you are going to be unbounded. That's what we club all those fixed y in one case and say regardless of all y greater than 0, you are strictly, I mean, you are guaranteed to go unbounded. Okay, so to answer your question, it's about both. For which y and for all possible x, it is supremum is going to give you some finite number, and that is the number that is a valid outcome for f star y. Okay, that is how we will define the domain of the function in a right way. Okay, so
Hello, sir.
Yeah.
So, if you consider a y which is finite over all x, but consider there exists a x for which that y is infinity, then we don't consider that y, right?
Now we eventually consider all y, right?
No, sir. Like I'm saying, there's a y value for which if we do supremum, we will be getting one infinity, like for 1x we will be getting infinity. So then we will not consider that y, right?
We will not consider that y, yes. So that will be kept out of the domain of f star, exactly.
Yes. What I was thinking is we will remove that x. I was thinking for which x
No.
leading to infinity.
Our goal is to find domain of f star, not x. We are removing y's. What are the possible y's?
So
What are
domain,
not possible y's?
so every element in domain of f star should give supremum bound. Supremum should be bounded for all x belongs to R.
All x belong to not R, but the domain of f. In this case, it's R++.
Yeah. Yes, sir. Yeah. The domain of yes, sir.
Yes. Yeah, it's a little bit tricky, but if you go through this, but we have a lot of more examples. So let us see. Okay, we will play with 3 more examples, and I will ask my TA to also do some more. So let us play with some other. Oh, isn't this already time? Yeah, it is already time. It seems like it's 2:30 already. Okay, so I think we started 1, right? So we will continue with this in the next class. So conjugate is important, as I said, because it's used in the duality. Duality is a very big business, especially let us say if you want to solve problems like SVM. Okay, SVM support vector machines. Those are constraint problems, and those require duality. Okay, so support vector machine is one of the important areas in machine learning. Okay, that's the very important model. Those are constraint problems, and then we need duality. Okay, so